Good evening, children. Let us start. This is assignment number 2. Numericals were mostly simple. First numerical, calculate mole fraction of ethanol in an aqueous solution containing 46% ethanol by mass. Say solution is 100 grams. 46% means out of 100, 46 grams is ethanol and remaining 54 grams is water. Now convert these masses into moles. Number of moles of ethanol, 46 by 46. Number of moles of water, 54 divided by 18. 3. So mole fraction of ethanol will be 1 divided by 4.25. We'll be a bit fast in discussing assignments, so please note down as fast as you can. Second numerical. When 200 grams of a solution containing 30% solute was pooled, a part of the solute precipitated out. Leftover solution contained 12.5% solute by mass. Calculate the mass of solute that precipitated out. See. B for solute, right? We'll calculate initial weight of solute which is present in the solution. It is 30% of 200. 30% of 200. 60 grams. Say weight of solute precipitated out. Let us say out of 60 grams, X grams of solute precipitates out on cooling. Therefore, weight of solute left 60 minus X grams. Weight of solution left. Earlier it was 200 minus X. So finally, this is weight of solute left. This is weight of solution left. And finally, weight of solute in the solution is 12.5%. Now I'll use the formula of percentage. 12.5% is equal to weight of solute divided by weight of solution into 100. Calculate X. X will be your answer. Third numerical. Mole fraction of acetic acid in a solution containing 46 grams of ethanol, 90 grams each of acetic acid and water is. See, if the numerical is very simple, I may sometimes skip. Like third numerical is very simple. I expect you'll be able to solve yourself. Coming to fourth. Calculate the amount of glucose required to prepare 250. Even this you can solve, no doubt. It's very, very simple numerical. And please do not expect such a simple numerical in the exam. Fifth, calculate molality of the solution prepared by mixing 40 cc of 1.2 molar and 60 cc of 0.8 molar solution of the same solute. Not very difficult, easy numerical. We'll be using M1 V1 plus M2 V2 is equal to M final V final. One solution is 40 cc. Molarity 1.2. Second solution 60 cc. Molarity 0.8. Final molarity we have to calculate. Final volume will be 60 plus 40, 100. This M will be the answer. Sixth numerical. 250 cc of an aqueous solution, density 1.1, contains 15 grams of urea. Calculate its molality and molarity. Okay. Weight of solution 250 into density. So weight of solution is 275 grams. Weight of A means solvent. Weight of solvent 275 minus urea is 15 grams, 260 grams. Now we can calculate both molarity and molality. In both, weight of solute 15 divided by molecular weight of solute 60 into 1000. This is common in molarity as well as molality. Now in molarity, denominator is volume of solution. Volume of solution is 250. This is one answer. In molality, denominator is weight of solvent. Weight of solvent is 260. This is second answer. Then seventh numerical we did in the class also. When I was teaching about normality, we did that in the class, exactly the same data. So that you can see notes. Last numerical. Calculate density of a 6 molar aqueous solution of NaOH containing 20% NaOH by mass. 20%. Okay. Say solution is 100 grams. 20% NaOH. It means out of 100, 20 grams is NaOH. Remaining 80 grams is water. Volume of the solution will be weight divided by density. Density we have to calculate. So it will be 100 divided by D. This molarity density we have to calculate. We are given molarity of the solution 6. So we'll use the formula of molarity. Molarity is equal to weight of solute divided by molecular weight of NaOH is 40 into 1000 divided by, this is volume of solution. E will be the answer. Now coming to theoretical questions. First question is, what is the significance of Henry's law constant? Its significance is that higher the value of KH, lower is the solubility of the gas. Right? For any gas, if KH is high, solubility of the gas will be low. That is the significance. Second, why a soda water bottle fizzes when opened at room temperature and pressure? This is based on Henry's law. When we open the bottle, pressure of CO2 on the surface of liquid decreases. Therefore, solubility decreases and dissolved CO2 gas escapes in the form of bubbles. Next, why is molality preferred to molarity in chemical calculations? The reason is it is independent of temperature. It does not vary with temperature. Last question. Give a general example where solubility decreases with increase in temperature. General example. See, generally means exceptions are there. Generally, when we increase temperature, solubility increases. But we have to give the exception. General exception is solubility of gases decreases with increase in temperature. Right? The answer is solubility of gases decreases with increase in temperature. Right, children, we start with the teaching part, notes. Right on, next topic. Next topic is Raoult's law as a special case of Henry's law. Raoult's law as a special case of Henry's law. It's a very small topic. It has always been there in the syllabus for the past 30 years, more than 30 years, but question has never been asked on this. Very small topic. Adam. According to Raoult's law, PA is equal to P naught A chi A. According to Henry's law, Pg is equal to KH into chi g. You already studied about both these laws. These are the expressions. Now look here. I'll explain. It will take few seconds only. Very small topic. See, if we compare these equations, you can see partial vapor pressure of the liquid is directly proportional to mole fraction of that liquid in the solution. Similarly, partial pressure of a gas is directly proportional to mole fraction of that gas dissolved in the liquid. The only difference is these constants. These constants have large difference in their values. Why the values of these constants are largely different? The reason is, in this case, liquid is much less volatile compared to the gas. This is for the gas, this is for the liquid. And gas is much more volatile, liquid is much less volatile. That is why values of these constants are different. Otherwise, there's no difference between these two equations. Now write down a comparison of these equations shows that partial Vp of a liquid as well as partial pressure of a gas are directly proportional to their mole fractions in the solutions. Constants P0A and KH have different values because the liquid is much less volatile than the gas. Thus, Raoult's law becomes a special case of Henry's law if values of these constants are same. So as I said, question has never been asked in the past. Next topic is ideal and non-ideal solutions. Ideal and non-ideal solutions. Today there will be no numerical to solve during the class. It's totally a theoretical topic, but an important topic. First I'll explain, then I'll dictate. See, like we say, so-and-so child is ideal. What does it mean? Ideal means we normally have the feeling, if we say the child, please do this, he or she does that. It means obeys elders. Similarly, we can say an ideal solution is the one which obeys Raoult's law. Opposite of what I tell you about ideal will be non-ideal. It means, what is a non-ideal solution? Which does not obey Raoult's law. Now, what is the meaning of obey Raoult's law, does not obey Raoult's law? Look here. You know about this expression, Pa is equal to P naught chi A, Raoult's law. Pa is the vapor pressure, partial vapor pressure of A, which we are expecting on the basis of Raoult's law. It means on the basis of Raoult's law, we expect that partial vapor pressure of A should be P naught A multiplied by its mole fraction. It means this is the expected value of partial vapor pressure of A. And on the left hand side, let us say this is the experimentally determined partial vapor pressure of A. Now, if I say ideal solution obeys Raoult's law, it means experimentally determined partial vapor pressure is exactly equal to what we are expecting on the basis of Raoult's law. But if experimental value does not match the calculated value on the basis of law, if this is not equal to this, then we'll say it is a non-ideal solution. When we mix, one thing more, this topic is for liquid solutions only. Partial vapor pressure of anything depends on forces of attraction between particles, right? If forces of attraction between particles are weak, its tendency to form vapors will be more, vapor pressure will be more. If attractive forces are strong, tendency to form vapors will be less, partial vapor pressure in the solution will also be low. Now, attractive forces between particles depend on two factors. Attractive forces between particles depend on two factors. One factor is surface area of molecules. More the surface area, stronger are the van der Waals forces of attraction. If you remember, you might have studied in 11th standard. I'll repeat, more the surface area of molecule, stronger will be the van der Waals force of attraction. Second factor is polarity. Polarity, positive pole, negative pole. Bonds are polar. You studied about chemical bonding in 11th standard. So if polarity of molecule is high, then attraction between positive pole of one molecule and a negative pole of the other will be strong. So in short, I can say forces of attraction between molecules depend on surface area and polarity of molecules, right? Now, if I mix two components, look here, this is pure A, attractions are between A and A only. This is pure B, attractions are between B and B only. When I mix these two to form a solution, new attractions between A and B will be formed. Now, if attractive forces between A and attractive forces between B and B are equally strong, I'll repeat, if attraction between A and A, attraction between B and B are equally strong, then the new attraction formed on mixing, new attractions between A and B formed, they will also be as strong as were initial attractions between AA and BB. We'll write it like this. For the time being, don't write anything. It means AA attraction will be equal to BB attraction will be equal to AB attraction. So after forming a solution, since new attractive forces between A and B are as strong as initial attractions, it means none of the two components will affect volatility of the other component, right? No component will change volatility, that is tendency to form vapors of the other component. Now coming to non-ideal. Non-ideal will be opposite. In this case, AA attraction in the pure state will not be equal to BB attraction in the pure state. Due to this, new attraction between A and B formed will also be different. And if new attractive forces formed after mixing are not as strong as initial, then there are two possibilities. These new attractions between A and B may be either stronger than initial attractions or maybe weaker than initial attractions. If these are stronger attractions than initial, then tendency to form vapors will, somebody tell me, then tendency to form vapors will say something. Decrease. Right? Okay. So if new attractions between A and B formed are stronger than initial attractions, tendency to form vapors will decrease. This will be called a negative deviation from Raoult's law. And the other will be opposite. If new attractions formed are weaker than initial attractions, then tendency to form vapors will be more. That is, vapor pressure will be more than the expected value. In that case, we call it positive deviation from Raoult's law. Right? So we start writing. There'll be a lot to write today. So heading is ideal and non-ideal solutions. Write down. Liquid solutions. Liquid solutions may be classified into ideal and non-ideal solutions. Ideal and non-ideal solutions. Please do the numbering the way I tell you. That an A part. Ideal solutions. Ideal solutions. That are those whose each component obeys Raoult's law over the entire range of concentration, so that the actual that is experimentally determined partial VP of each component.
Excuse me, sir.
Ah,
Sir, can you repeat from entire range of?
Need
Thank
please
you.
write a little fast. Doesn't matter handwriting gandi hai, it's okay. But so that
Okay, sir.
it will
Sorry,
affect
sir.
everyone. Okay, I'll repeat. So that the partial VP of each component, I'll repeat, obeys Raoult's law over the entire range of concentration, so that the actual, that is experimentally determined partial VP of each component is equal to what is expected on the basis of Raoult's law. That is, now copy from the board, that is PA is equal to P naught A chi A and PB is equal to P naught B chi B. Next paragraph. A solution will be ideal if molecules of both the components have approximately same surface area and polarity of molecules. Surface area and polarity of molecules. Under these conditions, Under these conditions, copy from the board. AA attraction will be equal to BB attraction will be equal to AB attraction. Although I have explained earlier, I'll explain again taking some other example. Look here. Let us say these are two friends, and they hold each other with a specific force. This is another pair of two friends hold each other with a specific force. Attraction between this pair is equally strong. Right? Now, if one of these two and one of these two, they hold each other with the same power which they were using earlier, it means the new attraction between A and B will be as strong as were the initial attractions between two pairs. That's what is happening here. New attraction between A and B will be as strong as initial attractions. And if this is the case, A will not affect volatility of B and vice versa. Tendency to form vapors will not change. Partial Vp will be equal to what we expect on the basis of Raoult's law. Right, on next paragraph. Since new AB attractions formed are as strong as AA and BB attractions in their pure state, no component affects volatility of the other component. Volatility of the other component. Next paragraph. For ideal solutions, delta H mixing is equal to 0 and delta V mixing is equal to 0. What is the meaning? Why it is 0? That is never asked, but this I'll explain. Right? It's simple. You should know what is the reason. One thing, if I say that for ideal these values are 0, for non-ideal, understood, these values will not be 0. Right? That will take up later on. Now, in this case, don't write anything. I'm explaining why these values are 0. First, let me explain delta V is 0. Delta V mixing is 0 means what? If I mix 10 milliliters of liquid A with 10 milliliters of liquid B, then final volume of the solution should be 20 milliliters. It means final volume minus initial volume. This difference is 0. Now, why it is so in this case? Why can it be other than 0? Everything will be clear. See, how much is the volume occupied by any substance, any given quantity of the substance, that depends on forces of attraction between particles. If attractive forces are strong, particles will be closer, volume occupied will be less. If attractive forces are weak, particles will be away from each other, volume occupied will be more. AA and BB attractions are equally strong. When they are mixed together, new attractions between A and B formed are again equally strong. It means after mixing liquids A and B, distance between molecules of A and B neither decreases nor increases because forces of attraction remain equally strong. This is the reason final volume will be exactly equal to initial volume. Change in volume will be 0. Second part is delta H mixing 0, means when we mix two liquids A and B, if the solution is ideal, there's no enthalpy change. Why enthalpy change is 0? Look here. When I mix A and B, I told you this probably 2 times earlier also. B will come in between A and A. That is, AA attraction will be broken. And to break this attraction, AA attraction is broken, two A's are separated. To break this attraction, let us say 10 joules of energy has to be supplied. Endothermic process means delta H will be positive. Similarly, in between B and B, A will come. BB attraction will be broken. B's will be separated from each other. In this case also, process will be endothermic. I'll have to supply some energy. Now, how much energy will be required? Since AA attraction and BB attraction are equally strong, it means in this case also, energy to be supplied will be same, that is 10 joules. So total 20 joules of energy has to be supplied. Two A's and two B's are separated. When they come in contact with each other, two AB and AB attractions will be formed. Since new AB attraction formed is as strong as AA or BB attraction, in this case, energy release will also be will be equal to what was the energy required to break the attraction. It means energy released exo will be minus 10 joules. And this will be twice. Why? 2A and 2B will combine to form two attractions. If you add them, net enthalpy change will be 0. Right? Now, later I'll have to explain about ideal and non-ideal. That will take up when we come to that particular part. Right? In that case, delta H mixing will not be 0. Delta V mixing will not be 0. That will take up later on. Next paragraph. Although no solution is perfectly ideal, but some examples of solutions which approach ideality, right? They're not ideal, but they approach ideality are: number 1, benzene plus toluene. Toluene is methyl benzene. Benzene plus toluene. Think hydrocarbons are non-polar, alkanes are non-polar. So both are non-polar, and surface area is almost same. Although surface area is different, but I'm saying almost same. So attractive forces are nearly same. Number 2, hexane plus heptane. Hexane plus heptane, again non-polar. There's a difference of only one carbon atom. There is difference in surface area, but not much. But at this point, listen very carefully. There's a difference of one carbon atom. That is why I said difference in surface area is very small. But do you think we can take the example of methane plus ethane? I'll say no, because difference in carbon atoms is 100%. So there'll be large difference in surface area when we talk about methane and ethane. If we talk about two alkanes, one containing 40 carbon atoms and the other containing 41 carbon atoms, that will form a still better ideal solution, because difference in surface area in terms of percentage, that will be very, very small, right? So third example, chlorobenzene plus bromobenzene. chlorobenzene plus bromobenzene. And last one more example, chloroethane plus bromoethane. Now we have to take up a graph. For the graph, first write one sentence, then I'll draw. VP graph, vapor pressure graph for an ideal solution is given below. Or an ideal solution is given below. While drawing, I'll explain also, and please do not stop, keep on drawing and keep on understanding when I'm explaining that. Y-axis, vapor pressure, x-axis, composition of solution. Now listen carefully. Let us say I have a very large size vessel. In this large size vessel, I take a very small amount of liquid A. Since it is pure A, it means mole fraction of A will be 1, mole fraction of B will be 0. Since there is no B, mole fraction of B is 0. One thing more, children, this is for the first time that I've adjusted my laptop at a certain angle so that I don't come in between Blackboard and you people. But are you able to read properly?
Yes, sir.
Okay.
Yes, sir.
Now,
Yes.
since pure A, there's no B. Since this is pure A, it means vapor pressure will be P naught A. So this is, let us say, P naught A. Now, to this pure B, vessel is very large. I've taken very small quantity of A. To this B, I add some liquid. To pure A, I add some liquid B. I add more and more and more quantity of B. As I keep on increasing B, mole fraction of A will keep on decreasing. Mole fraction of B will keep on increasing. It means, according to Raoult's law, value of PA will keep on decreasing, value of PB will keep on increasing. Let us say I add so much of B to A that A becomes negligible and it is almost pure B. At this extreme stage, it will be mole fraction of A equal to 0, mole fraction of B is equal to 1. It means from left to right, value of PA will keep on decreasing. Value of PB will keep on increasing. And when it is almost pure B, I'm saying almost pure B, then it will be P naught B. Now, what is the total vapor pressure of the solution at any intermediate composition? Let us say I want to find out vapor pressure at this composition. So at this composition, I should know values of PA and PV. I'll add them, I'll get the value of P total. What is this value? This value is PA and this value is PB. If I add this and this, there will be a point somewhere here. At this composition, tell me, what is this value? This is PB.
PV.
And this value will be PA. If I add, there will be a point somewhere here. It means these points will lie on the line joining P naught A, P naught B. So this line joining P naught A, P naught B will give the value of P total. Right? So this is the solution for ideal graph, the graph for ideal solution. Remember, values of P naught A and P naught B are not same. They are different. One is above, the other is down. So that is your choice, how you take it. Now, second part, non-ideal solution. P, non-ideal solutions. Now, for quite some time, I'll be dictating you directly. That will be opposite to what I dictated for ideal. I've already explained that. Right on. Are those which do not obey Raoult's law over the entire range of concentration, so that the actual, that is experimentally determined partial VP of each component is not equal to what is expected on the basis of Raoult's law. That is, PA is not, copy from the board, PA is not equal to P naught A chi A, and PB is not equal to P naught B chi B. For the right on, a solution will be non-ideal if molecules of both the components have large difference in their polarity and surface area. Under these conditions, again copy from the board, AA attractions will not be equal to BB attractions, will not be equal to AB attractions. Since new AB attractions formed are different than AA and BB attractions in their pure states, both components affect tendency of each other to form vapors. Means what? Volatility will be affected. Next paragraph. Non-ideal solutions are of two types. Now numbering will be small a and small b, right? Pattern A. There's no heading for small a and small b. A part. See, relax for a while, although I have explained earlier also. You have written that for a non-ideal solution, new AB attraction formed will be other than initial AA or BB attraction. I told you earlier, this new attraction between AB will either be stronger than initial or will be weaker than the initial attraction. Remember one thing. After initially, AA and BB attractions in this case are not equal. If new AB attractions are weaker, then these will be weaker than weaker of the two which were initially present. If I say AA attractions are weaker than BB attractions, then new AB attractions formed will be either weaker than AA attraction or stronger than a BB attraction. If you have confusion, I'll write. Let us say AA attraction is weak, BB attraction is strong, AB attraction. If this new AB attraction is strong, it means it will be stronger than these two. It means stronger than BB attraction. If these attraction formed are weaker, then this new attraction, this weak attraction will be weaker than these two. Weaker is this, it means this attraction will be weaker than AA attraction. Right on. If partial VP of each component is more than expected, solution is considered to show positive deviation from Raoult's law. Positive deviation from Raoult's law. Children, today's class may take 10 minutes extra, but we'll finish the topic. Now, when will partial VP be more? It will be more when attractions become weaker. And in such cases, AB attractions formed are weaker than AA and BB attractions, due to which their volatility increases. Volatility increases. Some conditions for the formation of this type of solutions are: number one, two liquids have different attractive forces like hydrogen bonding. It means both the liquids which we mix, both have hydrogen bonding, but hydrogen bonding in one is strong, hydrogen bonding in the other is strong. So when we mix this type of two liquids, then a solution with positive deviation will be formed, right? For example, ethanol plus water. Ethanol plus water. Number two, if one liquid has hydrogen bonding, but the other does not. Now I'll dictate you this one in detail. First I'll explain. See, if we consider alcohol, you consider any compound which contains OH group, it will have hydrogen bonding. It means all alcohols have hydrogen bonding. Water has hydrogen bonding. So if we consider ethanol, it has hydrogen bonding. If we consider any alkane, let us say cyclohexane or hexane, there's no hydrogen bonding. When we add cyclohexane to ethanol, hydrogen bonding will be broken. And new attraction between ethanol and cyclohexane will be weak attractions because they cannot form hydrogen bonding. For the formation of hydrogen bonding, both the molecules should have OH group. So hydrogen bonding will not be formed. So new attraction formed will be a weak attraction. It means positive deviation will be exhibited this by this solution. Continue. For example, ethanol has hydrogen bonding, but cyclohexane does not. When they are mixed, molecules of cyclohexane come in between ethanol molecules and weak attractions between ethanol and cyclohexane are formed. So weak attraction means positive deviation. Number 3, both liquids have large difference in surface area. For example, butane and heptane. Butane and heptane, there's a difference of 3 carbon atoms. So in terms of percentage, there's large difference in surface area. Number 4, liquids have, two liquids have large difference in polarity. Large difference in polarity. For example, chloroform and carbon tetrachloride. Last, one more example, one more case. Liquids are non-polar, but they have large difference in molecular weights. Large difference in molecular weights. Because if molecular weight is high, volatility will be less, right? For example, benzene plus CCl4, carbon tetrachloride. Now we have to take up the graph. Adam, next paragraph. VP graph for this type of solutions is given below. Now we'll quickly draw the graph for ideal. After drawing the graph for ideal, we'll make some addition. Chi A 1, chi B 0, chi A 0, chi B 1. This is composition of solution. This is PA and this is PB. And this is P total. You already drawn this graph. Now I'll add something to it. I'm waiting for you. I'm giving you 5 more seconds. Please complete it so that I can proceed further. So these 3 lines represent that we expect that partial vapor pressure of A should be this, partial vapor pressure of B should be this, total vapor pressure should be according to this line. But if there is positive deviation, it means partial VP of A as sorry, If there's if there's positive deviation, it means partial vapor pressure of A as well as B will be more than these expected values. We'll represent them with the help of dotted lines. So this is partial vapor pressure of B when it shows positive deviation. This is again on the higher side. This is partial vapor pressure of A when there is positive deviation. Sum of these two will be this. So this will be PA within brackets positive deviation. This is PB within brackets positive deviation. And this is P total within brackets positive deviation. It means when I dictate you, when I explain about negative deviation from Raoult's law, you will be drawing graph yourself. The only difference will be in negative deviation, these dotted lines will come downwards. They will come below solid lines. That's the only difference. Further write down, for these solutions, delta H mixing is equal to positive and delta V mixing is equal to positive. Delta H mixing is positive, delta V mixing is positive. Now, this is the part which I have to explain again. For positive, both values are positive. It means for negative deviation, both values will be negative. I'll quickly explain. First, delta V. If I mix 10 and 10 milliliters of A and B, after mixing in a positive deviation, new AB attractions are weaker. It means molecules of A and B will be at a little larger distance from each other than the distance between AA and distance between BB. Since AB molecules have gone little away from each other, it means final volume will be slightly more than 10 plus 10, slightly more than 20. Change is always final minus initial. Change in volume will be positive. Coming to delta H mixing. When AA attraction is broken, let us say 10 joules of energy has to be supplied. When BB attraction is broken, now since AA and BB attractions are not equally strong, this time energy required to break BB attraction will not be 10. It will be less or more than 10. It will be different. Let us say 12 joules. When new AB attraction is formed, I told you in case of positive deviation, new AB attraction will be weaker than weaker of these two. In this case, weaker is this. It means new AB attraction formed will be weaker than this. Value will be less than 10 will be released. So this will be delta H, let us say minus 9 joules. This I'll multiply by 2, add. You can see this will be positive. Right? So positive deviation, all values are positive. Negative deviation, opposite ho jayega, will be negative. All the values will be negative. Now, B part, small b. Now we are talking about negative deviation, will not take much time because it is opposite of positive. B part, if partial VP of each component is less than expected, comma, solution is considered to show negative deviation from Raoult's law. In such cases, new AB attractions formed are stronger than AA and BB attractions, so that volatility of both the components decreases. Next paragraph. Some conditions for the formation of this type of solutions are, now I'll give you 3 conditions. Number 1, when an alkyl halide is mixed with a compound containing oxygen or nitrogen or fluorine, within brackets, except alcohols.
So,
I'll repeat. When an alkyl halide is mixed with an organic compound which contains oxygen or nitrogen or fluorine, these are 3 highly electronegative elements, right? Then formation of hydrogen bonding decreases volatility. For example, chloroform is like alkyl halide. When chloroform and acetone are mixed together, they form hydrogen bonding as shown below, so that their volatility decreases. You'll draw it from the board. Remember, there's no hydrogen bonding in pure chloroform. There's no hydrogen bonding in pure acetone. But when they are mixed together, hydrogen bonding between them will be formed. Due to this, volatility of both the components will decrease. Vapors will decrease. It means it will show negative deviation from Raoult's law. Draw this. This is acetone, propanone, CH3COCH3. This is chloroform, CHCl3. I think on the basis of electronegativity, on the basis of displacement of electrons, if you look at arrows, it should be clear that hydrogen will carry slight positive charge because electrons are pulled by chlorine atoms. In this case, oxygen is more electronegative than carbon. Therefore, oxygen carries partial negative charge. So when they are mixed together, this is the formation of hydrogen bonding. So this is one case. Number two, aqueous solution of acids, aqueous solution of acids like sulfuric acid, nitric acid, acetic acid, etc. due to the formation of, so why do they show negative deviation? Due to the formation of ion dipole forces. Ion dipole forces. So there'll be attractive forces between H plus ion formed by the acid and polar solvent. So that is called ion dipole attraction. Last case, number three. Solution of a protonic acid. Protonic acid means acid which gives hydrogen as H plus ion. Protonic acid and a compound containing lone pair of electrons, which leads to the formation of hydrogen bonding. For example, when phenol and aniline, when phenol and aniline are mixed together, H atom of OH group of phenol and LP, lone pair of electrons at nitrogen atom of aniline lead to the formation of a strong hydrogen bonding as shown below. Strong hydrogen bonding as shown below. Why did I use the word strong? Reason is pure phenol has hydrogen bonding. Pure aniline also has hydrogen bonding. But when they are mixed together, new hydrogen bonding formed between them will be still stronger. So this will show negative deviation. Draw this one. Lone pair at nitrogen of aniline, H atom of phenol. Strong hydrogen bonding is formed. We are almost going to finish. Just one more minute. Next paragraph. For these solutions, delta H mixing is equal to negative and delta V mixing is equal to negative. VP graph for these solutions is given below. For that, leave some space and please draw it. After the class, please draw it. And last sentence, after the gap, write down. For all ideal and non-ideal solutions. For all ideal and non-ideal solutions, delta S entropy change is equal to positive and delta G free energy change is equal to negative. Right? So with that, we finish this topic. Next time, you'll have a different topic, right? Please keep on solving those MCQs. There are a couple of children who at times ask me solutions for MCQs which they are not able to solve. I expect everyone is trying. This will have difficult questions as well. Gradually, you will come across difficult questions. Devote time on an average, as I said, 10 questions per day should not be much for you, right? Bye.
Thank you, sir.
Thank
Bye,
you,
sir.
sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.